Hello everyone, we've got the last question, question 6, and we've got a static equilibrium question. So it says, figure 5 shows a uniform rod AB of mass m and length 2a. The rod has its end A on rough horizontal ground, so we've got friction going that way. The rod is in equilibrium and rests against a smooth fixed horizontal peg. So there's our peg P, and we don't need to worry about any friction because it's smooth, which also means that the reaction is going to be at 90 degrees. Okay, that's fine. It says the point C on the rod where AC is equal to 1.5A is the point of contact between the rod and the peg. So it's in contact at point C where this distance is 1.5A, that distance there. Okay, that's great. The rod is an angle theta to the ground where tan theta is equal to 4/3. So tan opposite over adjacent 4/3, and again we've got a Pythagorean triple there. The magnitude of the normal reaction of the peg on the rod at C is S. So S there is our reaction. Show that S is equal to 2/5 mg. Okay, so first of all, in order to do this, we need to take moments about A, because by so doing, we're going to eliminate our reaction force and we're going to eliminate our frictional force. Oh, by the way, I should have mentioned that in our diagram here, we've got our weight, it's a uniform rod, and the rod is of length 2a, so this distance is just a to the center of mass, and we've got a mass of m, so we've got our diagram there. So there's our theta and there's our theta. Now this is a bit that sometimes causes confusion to students. It's just knowing how to represent the forces going up here. And basically you can imagine that if I was to redraw this, so you can see that that is like a picture there of what's going on there corresponding, and these angles are vertically opposite. So you can represent the angle like that, and that's useful. The other thing that's sometimes confusing is students don't know how to complete this triangle. Well, in this particular question, we're going to be resolving vertically and horizontally. So I form my right angle triangle by drawing a line across that's parallel with the floor there. Okay, where that's my 90-degree angle. And you'll see more about that when we get a little bit further into the question. But for part A, we're taking moments about A in order to find out what S is. So the sum of my clockwise moment is going to equal the sum of my anti-clockwise turning moment. My clockwise turning moment is going to be A, the distance, times the force, which is going to be mg cos theta. So it's going to be A times mg cos theta. Cos theta is adjacent over hypotenuse, so 3/5. So we've got A times m times g times 3/5. Our anti-clockwise moment, now we don't need to do any resolving because the component of this force is already acting at 90 degrees because there's no friction. So therefore that's just going to be 1.5 A times by S. Okay, that's fine. So now we can cancel out A from both sides, and we've got that S is therefore going to equal, if we times everything by, times everything by 2/3, then that's going to get rid of the 1.5. So we've got 2/3 times mg times 3/5. The 3's cancel, and we get that S is equal to 2/5 mg as required. So that's our part A done for 3 marks. Now, the coefficient of friction between the ground and the rod is mu. Given that the rod is in limiting equilibrium, find the value of mu for 6 marks. Okay, so basically the rod is in limiting equilibrium, which means it's on the point of slipping down, which means that friction is acting towards the right-hand direction. So we're now going to resolve vertically and resolve horizontally in our diagram and see what we get. Okay, let's get our sketch there. So when I resolve vertically, let's consider the forces when we do that. So resolving vertically, what do we have? Well, we have the R plus S, and you can see why it's important that we've drawn this like this now, plus S cos theta is equal to mg. So the forces going up are R, S cos theta, and that is going to equal mg. Okay, so that's our first equation. Let's resolve horizontally now. Resolving horizontally, we have F is equal to this component here that's acting this direction, and that is S sine theta. So we've got F is equal to S sine theta. But remember, our F is mu R. Okay, that's fine. And if you remember that our R well, RR can be found by rearranging this equation here. So R is going to be mg minus S cos theta. Okay, so all I've done is resolved horizontally, F is mu R, and rearrange this to get R and subbed it in there. Okay, so far so good. Now, what else can we do from here? Well, we know also that S is equal to 2/5 mg. So this S now can be replaced by 2/5 mg. And the reason why that's useful is because when we do that, we've got an m and a g in every single term, which is super useful. So we now cancel the m and g because it's in every term. So that's fine. Leaving us with mu 1 minus 2/5 times by 3/5. Okay. Well, 2/5 times 3/5 is 6/25. 1 take away 6/25 is 19/25. So we've got mu times by 19/25 equals 8/25. So we times by the reciprocal of this fraction. So mu is 8/25 times by 25/19. The 25's cancel out and we're left with 8/19 as our value of mu. I think that was really quite nice. I think that, to be fair, that whole of Mechanics 2024 paper was very, very nice. And so was the statistics. So quite a nice applied papers, in my opinion, for 2024. I hope you found that helpful, and I will see you in the next video.